Okay, hello everybody. Today we will talk a bit more details about closed loop system and stability. So we have studied so far stability from the BIBO point of view or the bounded input point of view, and also stability in terms of the equilibrium points, and then we characterize those as the location of poles of my open or closed loop system depending on wherever you are. So what we will do today is to also look a little more details about feedback. Is feedback really helpful all the time, or there are some drawbacks? We'll skip the drawbacks part, or we'll will not go too much into the details, and we'll just see how feedback helps us in a lot of ways, and also define something called the relative stability. Okay, so open loop systems are heavily prone to disturbances, right. So the output is affected by the change in system parameters. The system parameters could be, like, if I am talking of a mechanical system, a mass could change, or any other thing could change in the system. It could also change because of external environmental conditions like temperature. Sometimes disturbances act into the system, and I really wouldn't know how to bring my system back to the original state. For example, if I am driving a car and my pedal is at a constant position, if I hit a ramp, or an upslope, that's a disturbance, right? And if I keep the same pedal position and I keep going through the ramp, I will not be able to maintain the desired speed, and after a while I might even lose the speed and I might just go to 0 speed, right. So there is no automatic correction if I set my pedal speed to its open loop value and just don't change it when the disturbance comes, right. Okay. In closed loop systems, the output is actually measured and compared with the reference signal, and which generates an error signal by which I update my control law, and through the control law I adjust my actuator, which gives the actual control input to the system, right. So typical things that could happen are, you have effect of disturbance, and you also have measurement noise, right. So my measuring devices may not be very accurate, and they might come with a bit of a noise. And so how do we deal with these things, the disturbance signal here and the measurement noise? So we want to keep or design our controller, or keep in mind such that I reject disturbances, and I also should reject the measurement noise. Okay. So let's start with an example, right. So this is a model for automatic control of speed for an automobile on a straight run, right. So I have a reference speed, I have the measured speed, and this generates an error signal which will decide the position of my throttle. Okay. So this is the throttle angle. There could be disturbances in terms of the road slope. It could either be a positive slope or a negative slope. No disturbance would just mean no slope, and this is a very simple model of my car, right. So the car, which looks very big with lots of components, actually looks very small here, right. It's just a first order differential equation, or a system with just one pole, and I just get the desired speed, right. So so this is like the standard measuring devices like the tachometer and all, and this will convert it to the appropriate speed. Okay. So the engine, for simplicity, is modeled as a first order system with a certain time constant and a gain of k with a typical value of 1.5. The input is the throttle angle measured in degrees, and the output is the desired speed, right. And the speed feedback is obtained by a tachometer, right, somewhere here. So this comes as in the feedback loop, and this is used to obtain the error signal for changing the throttle angle, right. And okay, for design purposes, we say that the throttle angle has a time constant much less than the system time constant, and therefore we could ignore it, right. And it is just modeled as a small gain k1, right. So the error signal via k1 gives me the control input. Okay. And some typical value we could assume in this case to be 50. The disturbance signal appears when the automobiles runs up or on a downslope, right, and it is expressed in terms of percentage of the road slope. So 90 degrees would actually mean that you are actually hitting a wall and just going vertically upwards. Okay. So and this signal is converted into equivalent throttle angle, and then you have this kg which takes care of the units, and you have this like kg is 100 degrees per unit percentage of the slope. Okay, so why are we doing this? So let us see if what happens if I just do not measure this guy, right. I have a reference and I just have the output, right, and there is no feedback, and also take the case of feedback. Okay, so given the first condition or the first problem that my reference or not reference, my desired speed is 60 kilometers per hour, that is in terms of the picture that would be V of s. Okay, so V of s is 60 kilometers, okay, or say V of t more nicely, and then we have to find the R or the reference signal with the system being first open loop and second being closed loop, and we can also see how the steady state error changes with this, right. Okay. So let us say in the open loop case, so at steady state speed is 60, and how will my transfer function look like? So it will be k1 times k over tau s plus 1, sorry. So this output is k1 k tau s plus 1 and some r of s. Okay, this will be a step signal, right. So I want to determine the size of the step. So let me just call it some number, say r over s, and I do the final value theorem, and I just get that 60 is this r times k1 times k, right, and then k1 was this guy 50, k is 1.5, and I do these computations and I get that r is 0.8, okay, that is kilometers per hour. Okay. Okay, now let us see what is the steady state error, right. So also if I look at in the Laplacian domain, right, E steady state, the Laplacian is r of s, the reference signal, minus y of s. Okay, so what we want to do is compare the errors, that is r of s minus y of s. Okay, so y of s here, or whatever is so y here is the velocity. So v of s would be equal to y of s. So y of s is again take this k1 k tau s plus 1 k1 tau s plus 1 over, this is by r of s. So the error is r of s 1 minus k1 times k by tau s plus 1, and at steady state, sorry, this error just becomes ESS. I do the final value theorem, limit s going to 0, s times ESS of s, that will just be so r is a step of some size 1 minus k1 times k. Okay, so this is my open loop error. Okay, so let us do the closed loop case. Okay, so in closed loop the reference is still 60 is R. I can just I'll directly write the steady state expression, right. So I just take get rid of all the transients, 1 plus k1 times k. So I'm just finding this one, right. I'm finding R in the closed loop case when the desired speed is 60. So I do all the computations and I get R as 60.8, right. The reference is again a speed. Okay. So now what is the error here is again I look at the signal here, right. That is again R of S minus output here is R of S k1 times k over 1 plus k1 times k. So this is R of S and just have 1 over 1 plus k1 times k. Okay. So just for simplicity assume that R is just 1. So in the open loop case, if I just say what is the steady state error, this would be for the values of k1 and k which were 50 and 1.5, this would be minus 74, and the steady state error here would be 1 over 1 plus 75, and this is significantly smaller than here, right. So I have a very big steady state error over here and I have a fairly smaller steady state error over here, right. So you see how the feedback or the closed loop reduces the steady state error. Okay. In the next case, let's do some transient analysis, right. So earlier we had done the steady state analysis. So we want to find in what time does the vehicle reach 90% of its steady state value for the open and closed loop system. So let's just do first for the open loop case. Okay. So in the time domain, I could write this directly. Vt is 60 1 minus e power minus t over 20. Okay. So this is like straightforward to write from the expression. Okay. So 90% of this value would be 54 is 60, and I want to find out the time, let me call this t1, at which this occurred. So I have an equation here where there is one unknown, so I can easily compute t1 to be 46 seconds. Okay. Now let us see what happens in the closed loop case. Okay. So in the closed loop case, so my let me just first write Vs is k1 times k over tau s plus 1 plus k1 times k. Okay. So this is multiplied by the R of S. Okay. So I just do some manipulations and computations. So in this case, my R of S for the closed loop, it comes from what I had computed over here. Okay. So this is 60.8. And then it's Laplacian, in the Laplacian it will be 60.8, whereas in the previous case my R for the open loop, when I will use this 0.8 kilometers per hour, right. So here when I do it here, so in the open loop case my R is 0.8 kilometer per hour, so just be careful of that. Okay. So now I just write down the final expression for V of t. I'll skip a bit of computations. So what I have 60 1 minus e power minus t over 0.263. Well, I just do nothing. I just substitute these values and then compute the inverse Laplace transform. And we now by now know how to do these things. So again this 90% would be 68. I have 1 minus e power minus, let me call this t2 over 0.263, and I compute t2, that is actually turns out to be just 0.6 seconds, right. So this is the open loop and this is the closed loop, and you see that this is 77 approximately times faster, right. So, if I just have a closed loop, my steady state error is much smaller, and also my response of the system is pretty fast. Okay. So, this will motivate us towards analyzing what are the effects of feedback on the system. First we saw, well, it helps in the steady state response, it also helps in the transient response. Okay. Are there anything else associated with feedback? Okay. Now, in the initial block diagram we mentioned few other things in addition to the reference and the output. So, one was the noise, sorry, the disturbance, and second was the noise. Okay. So, in the presence of disturbance and the noise, I can compute the overall output of the system or overall response of the system as the sum of response just to the reference signal, and while computing this I set d and n equal to 0, then I compute the response by setting r and n to be equal to 0. This will give me the response to the disturbance signal, and lastly for the noise I set the remaining two inputs to 0 and I just use the superposition. So, this is the total response to the reference signal, to the disturbance signal and the noise. Okay. So, let me just define the loop gain as Gc times G. So, if you have just forgotten where this Gc and G comes from, well, these are just these guys, right. So, Gc is my controller, is the plant, this is Hs is what happens in the feedback, I have the reference signal here, the disturbance and the noise. Okay. Okay. So, the error now becomes of course a function of what is the reference and something to do with the controller transfer function and the plant transfer function, similarly with the disturbance and also with the noise. Okay. So, I can just compute this directly, and these are, I think in one of the tutorial classes we saw how to compute the effect of disturbance and then take the total response of the system as the sum of the response to the disturbance and combine it to the response of the input, right. So, just a superposition. Okay. So, and when we started this lecture, we said, well, there could be some parameter variations, right, and then now we will see what is the effect of parameter variations on the system. Okay. So, assume there is no disturbance and noise, we will come to this very shortly. So, say my transfer function or the plant changes from G to delta of G. Okay. And then the error signal changes accordingly. So, I am just doing something very simple here. So, E, which is 1 over 1 plus L times R, L is Gc times G, I just substitute instead of G, G plus a small number delta G. Okay. So, this is how my error looks like, right. Okay. Now, the change in the tracking error can be computed, you can just say what is delta E, you take this guy here, and then E, I just substitute this guy, E is 1 over 1 plus L times R of S, and I get this expression, right. So, this is if again if delta G is 0, this goes to 0, right, that is the trivial case to check this. Okay. The change in the tracking error is something like this, Gc and delta G, and you have lots of terms of delta G influencing this this particular number. Okay. So, if I just take an open loop, right. So, I have, okay, I just for convenience I will just draw it here, and I hope I will use the right notation. So, this was R of S and this was C of S. Okay. Now, the error is usually defined as R minus C of S. So, in this case this is R, I will just omit the S for the moment, C Gc times G times R. Okay. Now, E plus delta E in our case turns out to be R, okay, R 1 minus Gc, G plus delta G. Okay. So, this is how my error looks like, and therefore, delta of E would be this guy minus the original error. Original error was what? That was 1, the R 1 minus Gc times G, all with in the S domain. Okay, if I just compare these things, so I just subtract this from this, so what I am left with is minus Gc times delta G. Okay, let me write this S here. Okay, this is also in S. Okay, so this is again in the open loop. Okay. Now, just me compare to what happens in the closed loop. So, I have the error signal is, of course, so I do some approximation that Gc times G is much larger than the very small change, and I get an approximate expression like this, that this is the change in error is Gc times delta G 1 plus L whole square times Rs. Okay. So, if you compare this with this, you see that the tracking error is reduced by a factor of 1 plus L of S with the square. Okay. And for large values of L of S, I can just again ignore this 1 and just write Ls, and I just get this expression. Isn't this is not difficult to obtain, right? So, the way you do this is you have minus Gc and you have a delta G, just ignore this 1, I have just keep this L of S here, and L of S is again Gc times G, right. So, this guy goes away and you have a R of S, and this is what remains, right. You have a delta G and a G, and right. And then okay, so what does this mean? That large values of L of S result in smaller changes in the tracking error. Okay, is there something which I could change in L of S? Well, so L of S, if you just recall, was Gc of S times G of S. So, one could that could be, well, change the plant, where I really don't want to do that, right, because the plant is already there is something which I am given to control, I just cannot change the subject or the plant. So, I can just manipulate my Gc in such a way that it results in smaller changes in tracking error. Okay. So, this is about how feedback changes the error or helps in reduction of error. Okay. Now, so what we saw was essentially this delta E related to small changes in the system parameter. Now, let us try to quantify that a little more, right. So, we call the system sensitivity. So, we will define this new term as the ratio of change in the transfer function to the change in the process transfer or some small parameter. So, I have the T as a transfer function. So, let us just understand it from here. So, I want to check how my overall transfer function changes with small changes in G, right. So, this is what I call as the sensitivity. This is S, how sensitive is the transfer function T to changes in G. Okay. So, what is T here? This is my closed loop transfer function. Okay. So, the sensitivity I define, so from here I just ask dt by dg over T of G. Okay. And this is how it looks like. Sensitivity of my transfer function with respect to G or changes in G is simply this one. Okay. Okay, let me go here, right. Okay, again I just start with I am just looking at the sensitivity with respect to disturbance, right, in which case I set the reference and the noise to be 0, and I can compute the tracking error, right. So, this is E of S is minus G 1 plus L of S. So, if I were just to write the sensitivity in terms of L, this would just be 1 over 1 plus L, where L is again what I call as the loop gain, L of S, and then just to recall again, L of S was Gc of S times G of S. Okay. So, this is my error with respect to disturbance, and it takes this term, right. So, 1 over 1 plus L is the sensitivity of the transfer function which changes in G times G times D, right. Okay. If Gs is fixed, which is usually the case, then with increase in the loop gain, so I want to reduce the error, right. Typically my error should be 0. If there is disturbance, there should be no error, right. So, how do I, well, but then if I have a disturbance, I would expect that there is some error. So, if there is some error, I would want to minimize the error, right. So, if Gs is fixed, then with increase in loop gain, this guy, the effect of disturbance can be decreased, right. Okay. So, something which I will briefly introduce now is, okay, so is something related to frequency. We will talk a little more of this when we talk of frequency domain. So, disturbance signals are typically signals of low frequency, right, maybe like a step or even if they is oscillatory behavior in the disturbance, they will just be at a very low frequency. In the car example, my disturbances are either I hit a uphill or a downhill or something like, it will just be the constant thing without any disturbance, right. So, disturbance signals are mostly introduced, or these usually occur at low frequency, okay. So, my L is, okay, if I just look at how it varies with frequency, I can just see the magnitude of L at frequencies, right. So, at low frequency, so I want, so what does it say that, or this expression tell me that with increase in loop gain, the effect of disturbance decreases. Now, I do not have to increase it like forever, right. So, L I know depends on frequencies, and my disturbance signals are associated to certain frequencies or certain lower frequencies. So, I want G to be, sorry, this L to be increased at low frequency. So, this should be bigger for lower frequencies, okay. So, this essentially means that I increase the controller gain at low frequency, right, or in other way I am just, so if this increases, my sensitivity decreases. So, ideally I would want, I do not want to be sensitive to disturbance, right, whatever happens I just should reject it, okay, but typically that does not happen, right. So, we can only decrease the sensitivity. So, when I try to increase this at low frequency, my sensitivity decreases, right, at low frequencies. I do not really care what happens at high frequencies at the moment, because there are no disturbance signals which come at high frequencies, okay. Now, what about this noise, right, we so far have not talked about it, but then usually my measurement comes with some noise, right. Okay. So, tracking error in terms of the measurement is something like this, right, again it is from the original expressions which we obtained. So, this guy L over 1 plus L is also known as the complementary sensitivity function. So, some people denote it as T, some people denote it as C, and since we have already used the notation T and C, we will not use it, we will just say this, maybe just for, I can just call this S prime, the complementary sensitivity function, okay. And this noise, so small loop gain, if L is very small, it leads to a good noise attenuation, right, because this the effect of noise would be reduced. And typically noise signals are signals which occur at very high frequency, or which get into the system, and these signals are typically high frequency signals, okay. So, for the purpose of noise attenuation, the loop gain is turned to be low of low values at very high frequency, right. Previously what we had, that I want the loop gain to be higher at lower frequencies, that will eliminate my disturbance. For the purpose of noise attenuation, the loop gain is tuned to have lower values at high frequencies, right. So, when I do this, the controller gain is increased at low frequencies for disturbance rejection and decreased at high frequencies for noise attenuation, right. So, it is like some kind of a complementary effect over there, right. So, these are the two ways which, based on what is the L of j omega, I can deal with disturbance and noise together, or reduce the effect of disturbance and the effect of measurement noise. We will do more of this when we do frequency response, right. What does actually mean, what is low frequency, what is high frequency, and so on, and how do I actually go about computing these things. That we will keep till a little later when we do frequency response analysis. Okay. And something which we will use throughout from now on is what is called as the characteristic equation, right. So, what is the characteristic equation? Well, it is just I take the transfer function and I look at what is in the denominator. So, I know how to compute this, right, given g in the forward loop, h in the negative loop, the overall transfer function T of s from R to C is g over 1 plus g, Okay. So, the transfer function, sorry, the characteristic equation is when I equate the denominator of this guy to 0, right, 1 plus g times h equal to 0. Okay. And so, if h equal to 1, then I am having like kind of something very simple, right, 1 plus g of s equal to 0. Okay. So, now this is a system with a non-unity feedback. Now, is it possible that I do some magic and I convert this to a system which looks like this? Let me call this g prime of s, sorry, there is nothing here, erase, okay. So, and then plus a minus with this to be 1, this guy still being r and this guy still being c, right. So, I just want to convert this non-unity feedback system to a unity feedback system. Can I do this? Well, the answer is yes. So, what I do is I just equate. So, how will this transfer function look like? That is simply g prime of s over 1 plus g prime of s, and I find out what is g prime in terms of g and h. Okay. So, a non-unity feedback system can be transformed into a unity feedback system by just using this transformation. This should be very straightforward to compute because you are just dealing with very easy looking linear equations over here. Okay. So, g prime would be this one, h prime would be 1, right. And while I do this, the characteristic equation remains the same. So, if I just look at 1 plus g prime h prime of s, this is 1 plus g prime of s, and I will just get this. This again simple computations will take you from 1 plus g prime h prime to 1 plus g times h, right. This is nothing special happening over here. Yeah. Okay. So, let us revisit stability for a while. Right. So, I start with the system that looks like this, right. So, this is, I know that this is stable because I have, sorry, this is unstable because there is a pole on the right hand side. So, anything on the right hand side unstable, right. So, can I do something with this, right? Can I do something so as to make this system stable? Well, I just say, okay, I just take the negative feedback h of s just to be a number 3, and I take the closed loop transfer function, set the characteristic equation to 0, and the poles of the closed loop system are now minus 1 by 2 plus minus j root over 3 by 2, right. So, these are complex conjugate poles, but which are again in the LHP, right, in the left half plane, right. So, this guy. So, all poles are to the left half plane, and therefore, the closed loop system is stable, right. So, I start with an open loop system which is unstable. I can stabilize it with just some feedback, right. So, this is one advantage which I get when I do feedback, right. I can make unstable systems stable. Is it possible always that give me any unstable system? Can I make it stable via feedback? Well, that may not always be possible, but it in several cases it is possible. Okay. So, what are the advantages? Okay, advantages is I can see that I can have improved stability, I can have decreased sensitivity to parameters, I can deal with disturbances, I can deal with noise, right, and we could also increase bandwidth. We will see this when we do the frequency response of the system. But then my overall gain of the system reduces, right, because I have some multiplicative factor over there, right. So, here, so okay, I'll go here and okay, this kind of gives some attenuation which may not always be desirable. So, that is one of the drawbacks, and of course, I would have increased cost to deal with, and sometimes a bit of complexity too, but of course, the advantages are a lot more compared to the disadvantages. Okay. So, sometimes now we have seen how the system could be sensitive to change in parameters, right. So, we will see does that have any effect on stability, and that is called relative stability, right. So, at the moment we just talked about is the system stable or unstable, right, nothing more, right. So, now given a system, can we define some kind of a relative stability? Relative stability means can a small change in the parameter of the system make it unstable, right. And then that we will define it as the, there will also be some measures of stability, that if my system parameters are between so and so, I could still be stable, right. So, for example, if I am making cooking food, and the I just download something from some khana.com or all those websites, and they say okay, 1 tablespoon of salt. But if I just put 1 tablespoon plus 1% or minus 1%, it does not really kill the taste, right. But if I put 2 tablespoons, that might be awful. If I put 0 tablespoons, that might still not be very good. So, but then there is some amount of relative stability, right. You can go slightly higher or slightly lower and still maintain stability, right, stability in terms of the taste. But if I am making tandoori chicken and it says put on the oven for 20 minutes, but if I say 22 minutes, then I might not really get something very edible, right. So, that little thing could be unstable over that. Okay, 20 minutes 1 second could be okay, but if I do 20 minutes plus 2 more minutes, that could give me something very strange, right. So these are things which changes in little parameters sometimes affect stability, sometimes wouldn't affect stability. So if I am looking that I'm playing a cricket match and my team is chasing a score of something in some 20 overs, and at the end of 15 overs I am I still need 40 runs with 5 wickets in hand, I could still say, well, I can still win the game, right, because my required rate is not too much. But all of a sudden if I lose 2 wickets, right, then that could be a recipe for disaster. I could go from a winning zone directly to a losing zone, right. So these are things where you are stable, and you can all of a sudden become unstable, and that is exactly what is the concept of relative stability. Okay, so we do not really deal with food or sport here, we deal with physical systems. So what does it mean in our case, right? So we look at our stability in terms of the location of the poles, right. Well, typically complex poles or real poles or whatever, right. So what I said is in terms of systems, if I say, well, I am here, so these are my poles, and I say I have a system which typically would look like this, K, a G, a H, a plus, a minus, this is my R, this is my C or the output. And say I design my system, I work very hard, and I say, well, my system is stable, it has poles at plus minus 0.1, sorry, not plus minus, it should only be minus. Okay. So I am given a fantastic design problem, and I just say this, my poles are at 0.1 plus minus j whatever, say 2, right. I work very hard and I submit this as my thesis, and I say my controller works because my poles are here, right. So these are my poles, okay. And 2 days later, my supervisor comes and checks it, something would have gone wrong there, right. My mass would have been a little different than earlier, or some rats might have chewed on to something where my mass slightly decreases, and when I run the system again, so maybe these guys just jump here, right. Or maybe I did it in an air conditioned environment, the power goes off, and I am presenting this to the examiners or my supervisor in a different environment where the parameters might change, and say, oh, what I see, the response, oh, so it goes unstable, right. So my poles could just be, instead of minus 0.1, it would just be 0.1 plus minus j2. This could happen, right. So, and we will see there are lots of cases where this will happen, and therefore when I design things, I will say, well, I don't want stability, I want something like more stable, right. It's like this, right, somewhere. Okay, so I want my poles to be somewhere here, so not just left of 0, but say at minus 1 or further left of minus 1. So I want to be to have a little buffer for myself to do these things, right. Okay. So these are things which we can talk about, of relative stability. Now, do we have any tools where I can say where we can actually quantify relative stability. We have learned the Routh table, right. So, let us see if I could say something about relative stability. May not be very useful in terms of exact analysis, but some preliminary analysis I could do about relative stability, right. Okay. So, I have a closed loop characteristic equation where I just factorize them in terms of n poles, right. So, there is a direct relation over here. So, the relative stability can be determined by using Routh-Hurwitz criterion by just shifting the axis, right. So, if I say start with this guys, say consider a system, a third order system, and I say is it stable, I do the Routh thing and I say everything is positive, 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 no sign change, and therefore my system is stable. Okay. But this does not help, because if my temperature changes slightly or some little thing goes wrong here and there, then I go to unstable. Therefore, I will pose a slightly different problem to be a little more comfortable. Okay. And I say, well, are the plane, so are all the poles over here are they at left of -1? Until now I was only interested in left of 0. But if I have at -1, I have a little margin here, right. So, even if the temperature increases, which shifts the pole maybe from -1 to 0.8, I am still stable, right. And therefore, I want to push them as slightly further to the left. Okay. So, the way we check this is like this. So, let me define a new variable called S1, which is S plus 1. Okay. So, my S now will become S1 minus 1, okay. And I rewrite, so this is my new coordinate frame where the origin is -1, 0, okay. So, if I take a characteristic equation which is S plus 2 equal to 0, which has a pole at -2, how will this pole look in the new coordinates, okay. So, my S is S1 minus 1 plus 2 equal to 0. This means I have S1 plus 1 equal to 0, which is okay, right. So, in my new coordinates, sorry, in my old coordinates I was at a distance of -2 from the origin. If this is the new origin at -1, I should be at a distance of -1 from the new origin, right. So, that is just what this guy tells us. So, simply put, if I were to check for a general polynomial here, so are the roots of this equation to the left of -1, I just substitute this guy, right. So, in the new coordinates S1, I just do this substitution, my characteristic equation looks like this. Now, I do the entire Routh table thing for this one, right. So, okay, so it is a 1 and 4, 1, 4, so this row will go to 0, I will have an auxiliary polynomial and I will just solve for the auxiliary, differentiate this and then I do all these things, okay. So, first is there is no sign change and therefore, there are no roots on the shifted plane, there are no roots which are on the right hand side of -1. However, there are two roots here. So, we can say this is in some sense called marginally stable with respect to this axis. Of course, in the original coordinates it will not have a sustained oscillatory behavior, that we should be a little careful of. So, I am just saying, well, it is not left of -1, but there are a couple of guys who are just sitting on -1, marginally stable with respect to this new shifted coordinate, that is -1 and 0. Okay. So, what we have done so far is we started with the concept of stability, we defined some criterion for BIBO stability, we also found out how we given a transfer function, how I computed stability. Given then a higher order polynomial, we had an algebraic method to compute are there any unstable poles. We looked at closed loop system, advantages of feedback and some analysis on relative stability, some very basic analysis on how stable my system is. So, what we will do next is to focus on these kind of things of relative stability and see if there are more sophisticated analytical tools, which is called the root locus method. We will see how my pole locations respond which changes to certain things in the systems. So, these are essentially conditions derived by Even and called the root locus techniques. We will study some construction rules of this graph called the root locus technique. Okay, thank you.